It is natural in decision trees to approximate continuous distributions with discrete distributions. For example, if a chance node indicates the level of sales resulting from some advertising campaign, it is natural to discretize the possible sales levels as, say, high, medium, and low. The reason is that you then have a manageable tree with just 3 chance branches. In reality, however, the sales level has a continuous distribution. Of course, it is not possible to have infinitely many branches emanating from a chance node, but it is possible to induce this behavior by using Atrisk in conjunction with PrecisionTree. The tree shown here indicates how you can do this. A company has to decide which of 2 advertising campaigns to use. The second not only costs a bit more, but it has a bigger upside sales potential and a bigger downside risk. The tree is different from the usual decision tree in the following respects. First, Atrisk is loaded, as well as PrecisionTree. Second, there is only one chance branch from each chance node. Its probability is 100%. Third, the costs of the ad campaigns in the orange cells are not simply numbers. Each is an at-risk distribution function. In this case, the log-normal distribution. Fourth, the sales levels in the yellow cells also contain at-risk distribution functions. Again, they are log-normal distributions. And finally, the green shaded cell has been designated as an at-risk output cell. Currently, Atrisk's dice button is toggled to static, not orange. So you see expected values in the tree. Based on these and the usual expected value criterion for decision trees, ad campaign 2 is favored, with an expected net gain of $50,000 versus only $40,000 with ad campaign 1. Note that this is the same information you would get if you replaced the ad campaign cost distributions with their expected values, and you discretized the sales level distributions using several chance branches in such a way that the expected sales levels are the same as shown here. So you might wonder what the advantage is to using at-risk functions. The advantage is that you can now run an at-risk simulation to see a more realistic histogram of the net gain from the best decision. I will run the simulation with 1,000 iterations. As you can see in the resulting histogram of net gain, the mean is practically the same as the value shown in the tree, about $50,000. But you also see a realistic range around this mean. If you use PrecisionTree in the usual way, with only a few representative values in the tree for the chance outcomes, the resulting risk profile from PrecisionTree would include only a few spikes, not the continuous histogram you see here. When you use at-risk distribution functions in a decision tree, you should understand a few settings. You find these by selecting Model Settings from the PrecisionTree Settings drop-down list and choosing the At-Risk tab. The most common options are those checked here. The first calculation option in the top section, Expected Values of the Model, means that on each iteration of the at-risk simulation, the simulated values will be entered in the tree, and then PrecisionTree will calculate the expected values from them in the usual way. The first forcing option in the bottom section, Decisions Follow Current Optimal Path, means that PrecisionTree will choose the same decision on each iteration, the one that is optimal based on expected values. In the current model, it always chooses Ad Campaign 2 because its expected net gain, $50,000, is larger than the net gain from Ad Campaign 1, $40,000. To illustrate this, I ran the at-risk simulation using these options, and I then captured the simulation data in this worksheet. Actually, I captured this datasheet earlier when I was developing this file. I calculated the net gains from the 2 ad campaigns in the last 2 columns. Differences between sales levels and cost of the ad campaigns. Note that the actual net gain from campaign 1 sometimes beats the net gain from campaign 2. But the at-risk output value in the second column always lists the net gain from ad campaign 2 because this ad campaign is optimal in terms of expected value. This makes sense. The decision maker sees which of the two ad campaigns has the larger net gain only after making the decision, so it wouldn't be fair to use this information when making the decision. However, it can be useful to check the second forcing option. Decisions may change each iteration based on expected values, because this is useful for finding the expected value of perfect information. I will select this setting and rerun the simulation. Here is the histogram of net gain, and here is the simulation data. Again, I captured this data sheet earlier while I was developing the file. As you can see from the data, the value of the at-risk output cell in the second column is equal to the larger of the two net gains to the right, the one I've colored yellow. This means that the decision maker can wait until the uncertainty is resolved and then make the decision. Of course, this is unrealistic, but this perfect information provides an upper bound on how much any information would be worth. From the histogram, the expected net gain with perfect information is about 64,800. Therefore, the expected value of perfect information is the difference between having perfect information and not having it, 64,800 and 50,000, or about $14,800. No information, imperfect or perfect, can be worth more than this. I will conclude this video here. If you are curious about the other at-risk options in the dialog box I showed earlier, specifically this one and corresponding options down here, further information is provided in the at-risk example file in the PrecisionTree example files folder.